Well, welcome again to Math 315, Analysis and Topology, and this is the first video for section 2 on limits of sequences and the monotone convergence theorem. So we're going to begin by looking again at sequences. We looked a little bit at sequences in the previous week, and we want to now try and pin down precisely what we mean by the concept of convergence of a sequence. And this is a difficult idea, and I'll do lots of examples, but it's one of those basic skills that you'll need to be able to do. So firstly, let's begin with a very simple sequence. AN is 1 over n, and it's intuitively clear, as we've seen before, that 1 over n gets closer to 0 as n gets larger. Graphically, we can draw little pictures here. So when n is 1, 1 over 1 is 1, then a half, then a third, then a quarter. And these are getting smaller, they're getting closer and closer to the axis here, the further out we go. Similarly, it's intuitively clear, just by common sense, that if I take n over n plus 1, so you think of 1,000,000 over 1,000,001, that's pretty close to 1, as n gets larger and larger. And again, I'll draw a little picture of that. So here we put in n equals 1, so I get a half, and then I'll get 2/3, and then 3/4, and so on. And this is getting closer and closer to this line at 1 here. Now the point is, exactly what do we mean by gets closer to? How close? And how far out do we have to go before we can say that we're close enough to this limit 1? And so we would like to capture the idea of the limit of a sequence of real numbers in a very precise way. Now again, we return to this example of this Bn sequence of n over n plus 1, and there's our picture again. So there's what we claim to be the limit 1. Here are the terms of the sequence. And what I'm going to do is I'm going to draw two little bands here. The engineers call these tolerance bands. So we think of epsilon as, this is a Greek letter epsilon, which is generally used for something which is very small. So I go up a little bit from 1 and I go down a little bit from 1. Now we generally have to go both ways, because for this sequence it's moving in this direction, but there are other sequences that might move in the opposite direction, or there are some that might wobble up and down. And so we normally draw our epsilon band both sides of the limit 1. So I go up a little bit, I go down a little bit, and I draw these epsilon bands. Think of epsilon as a number like 0.01. as being very small. Now if you look in the picture, you can see that, even in my rough diagram here, that eventually, provided I go far enough, the crosses, these terms of the sequence, move inside the band eventually, and they stay there the further out we go. They stay there forever, inside the band. So in other words, if we go out far enough, then no matter how small we make our little band here, the crosses will eventually move inside the band and they will stay there forever. Now I need to capture that idea formally, but just looking at the picture you can see that it sort of makes sense. So I tell you how wide the band is, I give you the epsilon, and you have to be able to tell me how far along, what's the m, how far along do I have to go, so that if I go further than that, then the crosses are all inside the band. Now how do I measure what the difference is between the two? Well, this little difference in here is going to be Bn minus the limit, which is 1, and then I better take absolute value in case, because that'll be in fact negative, but I want to measure this distance. So this is measuring the distance between the terms of the sequence and the limit. And I want that to be less than the width of the band, which is epsilon. Now I'll write all that down formally, but keep the picture in mind as we discuss this. So here's the formal, here is more formal way of writing what we've just been saying. We say that given epsilon bigger than naught, that is, I tell you how wide the band is, we can find, and we have to explicitly find it, a real number m, so that if I go past that point, if I take my n to be bigger than capital M, then the crosses are all inside the band. That means the difference between the sequence value and the limit, the length, the distance between the two, that's the absolute value of the difference, has to be less than the width of the band. Now this takes a bit of getting used to understand the geometry, and also then, as we'll see, actually applying the definition is not easy either, and I'll do lots of examples of this. Some of them are straightforward, some of them are a little bit more complicated. You will be expected to do fairly a basic application of this, and I'll do some examples shortly. So this number m then tells us how far we need to go until all the terms of the sequence after that are inside the band, inside the epsilon band. And we think of epsilon as being as small as we like. I tell you epsilon, I tell you how close you want to be to the limit. You have to tell me how far out I need to go to guarantee that. Now, just as a little note here, this m does not have to be as small as possible. It doesn't have to be the best possible m. Any m that works will do, even if there may be some better choice. And we'll look at this more later on, but just I'd simply mention it here. Let me just come back to our picture again. So what I'm saying is that in this picture here, I chose the m so that it would you were just inside the band, but I could have taken m to be up here or m to be here, as long as thereafter I'm inside the band. So we're not necessarily looking for the smallest m, and that may be quite difficult or fiddly to find, the smallest m. We just want any m that works. And the m, of course, will depend on epsilon. The m is going to depend, it'll be some function of epsilon, it's going to depend on how thin the band is. Now this is the key and difficult idea behind limits. And you have to get your head around this. It's not a particularly easy idea. Mathematicians struggled with this. The idea was first put forward by Cauchy. Using this, we can now make the following fundamental definition. So this definition should be learned carefully. And so you could, for example, be asked to reproduce the definition. This is such an important one. Applying it to a particular sequence can be harder, as we shall see. So I've left an I out there. So here's our definition. A sequence A sub n, this is just a collection of, think of it as crosses of real numbers as we move along, converges to a limit L if and only if, given epsilon bigger than naught, we can find a real number capital M, so that if I go past that point, if n is bigger than m, then the difference between the sequence and its limit is less than epsilon. This is a fancy way of saying the sequence is inside the band. So here's our picture again. There's my limit L. We've got these crosses. Now they may wobble around, they may do all sorts of things. So they might go up here, they might jump down, they might go into the band, then they might jump outside and go here and there. But eventually they settle down and they stay inside the band. That is, there is an m down here, so that if I take my little n bigger than m, if I take any of these crosses, then the distance between here is less than the width of the band. So that distance is given by this. It's an minus L. It's just this length here, and that's got to be less than epsilon, which is the width of the band. The sequence might come in from the top, or it might come in from the bottom, and that's why we have to draw both epsilon bands and why we need to take absolute value here. So you need to think about that and try and get that, at least the basic concept, into your head before we start to look at how to actually apply this formula or apply this definition. Now I just note here that some textbooks, in fact most of them, insist that this m has to be an integer. Well, this adds an unnecessary complication to the application of the definition. Because after all, in practice, if m is not a whole number, then all I do is I simply take n to be the next integer after m. And the desired conclusion is still valid. So if m is not a whole number, these n's here have to be whole numbers, of course. This is 1, 2, 3 as I move through the sequence. If m happens not to be a whole number, well, that's okay. I just go to the next whole number bigger than that. Because after all, the definition said n bigger than m. So if m is 3.5, then I'd take n to be 4 or bigger. So we will, as you've seen before, use this notation. The limit as n goes to infinity, that means as n gets very big, of an equals L. That's what the definition is enabling us to write down very, very explicitly. Well, let's actually I want to do a number of examples of this, and we'll see that it's not that hard to do simple examples, and we'll look at some more difficult ones later on. And there are lots of tutorial problems that we'll practice with this as well, because it's a basic skill. So we're going to prove from the definition that 1 over n has a limit of 0 as n goes to infinity, which is a result that we knew, and we're now going to prove this formally. So here's our proof of this, and here's my picture. So 1 over n, these terms are getting smaller and smaller and smaller. The crosses are going in smaller and smaller. So we start out, if n is 1, I'm up here at 1, then a half, then a third, then a quarter, and so on. And the limit here is going to be 0. So I draw my little epsilon bands, 0 plus epsilon, 0 minus epsilon. There's the two epsilon bands, just to see it. You don't need to draw this picture every time. I'm just drawing it here to try and cement in the ideas. So the crosses are going to move eventually inside the band, and you've got to tell me how far out I need to go. Now, what I do with this is I simply begin to write down the definition every time. So I begin with, given epsilon bigger than 0, put m equal to, I don't know yet. We'll find that out in a minute. So I leave a gap here at the moment. I'm going to cook up an m that makes the definition true. This is the way I'm going to set all of these problems out. Note that some books do this slightly differently, and I've seen some people do this slightly differently. I don't like the alternative methods that I've seen, because the logic is around the wrong way, and then you've got to worry about whether the steps reverse. It's just all too complicated. So I prefer to do it this way, but you may see in other videos, if you're looking at other things, or in books, funny other ways of doing this. This is my preferred way. So given epsilon bigger than 0, put m equal to, I'm not sure yet, I'll tell you in a moment. Then, if I go beyond m, then I need to show that I need to squeeze 1 over n minus its limit. I need to squeeze this less than the width of the band, which is epsilon. So I just plug it in, 1 over n minus the limit, absolute value. Well, n is positive, so this is just 1 over n. Now this is where we use this fact. What I aim to do always is to get rid of the n, the little n, and try and get something involving capital M. So if n, and everything's positive by the way in here, so no worries about negatives and things. So if I take 1 over both sides of this, then that flips the inequality sign around, as we mentioned in last week's class. which I'm sure you knew from school anyway. So if you take 1 over n, that's less than 1 over m. Now, how big did I want this? I wanted this less than epsilon. I've squeezed it less than 1 over m, and I haven't told you what m is yet, but now I do. I'm just going to make this equal to epsilon, because that will then, that's what I want, that will satisfy the definition. So an minus its limit is less than epsilon. And now I simply rearrange this equation here. This says 1 equals m times epsilon, so m is 1 over epsilon. I just solve this for m in terms of epsilon. You can turn both sides upside down if you like. M is 1 over epsilon. And now I've satisfied the definition. The definition was, I tell you how wide the band is, you tell me how far I have to go. So for example, if epsilon was 0.01, then 1 over that would be 100. So I'd need to go out to beyond the 100th term in order to get this sequence inside the band if the width of the band was 1 on 100. So I tell you epsilon, you tell me m. So I put m to be 1 over that. Then if n is bigger than m, then the sequence minus its limit in absolute value is less than epsilon. That's the definition. Now you might pause and think about that example very carefully before we move on, and we will do lots more of these in the tutorial. Okay, second example, slightly more sophisticated this time. We're going to look at this limit. So we're going to prove from the definition that 2n squared over n squared plus 3 has a limit of 2 as n goes to infinity. You would have seen from last week's work that you can see that the limit has to be 2. If you divide top and bottom by n squared, you see that the dominant term on the top's 2n squared, dominant term on the bottom's n squared. Who cares about the plus 3? So this is roughly 2. So you would expect the limit to be 2, and we're going to prove from the definition. Now just in the wording, when you're expected to do one of these definition proofs, rather than just doing it by looking at it, then I will explicitly say prove using the definition or using the epsilon m definition. So I'll be very explicit when I expect you to do it from the definition, as opposed to just using our more heuristic methods. And here's the proof of this one. So again, you just quote the definition. Given epsilon bigger than 0, put m equals 2. I don't know yet. I leave a little gap. I'll tell you in a minute. Then, if n is bigger than m, if I go past there, we want the sequence, that's 2n squared on n squared plus 3, minus its limit, and I want to squeeze this less than epsilon. So I simply, I've substituted in the sequence, I've substituted in the limit, and now I'm going to simplify this. So I put it over a common denominator, n squared plus 3. I get 2n squared minus 2 times n squared plus 3. Now when you take the brackets out, you'll get 2n squared minus 2n squared, that cancels, and you're going to get minus 6. Minus 2 times 3 is minus 6. So you take the brackets out and simplify it. Now I'm taking absolute value of that, so that's just going to be 6 on n squared plus 3. Now what I want to do is, I want to get this in terms of m. So you've got a choice here. You could just say this is less than 6 over m squared plus 3, put that equal to epsilon and solve, but you get, unfortunately, the trouble is you've got to worry about cases and things, and I don't like that very much. What I'd like to do is, I'd like to try and get this as a bit simpler. What don't I like at the moment here? Well, I don't like this plus 3. It's a bit of a pest here. So I'm going to get rid of the plus 3. And here's where we use inequalities. Inequalities is the art of throwing out the rubbish. That's a nice way of thinking about using inequalities. Inequalities enable us to throw out the rubbish. Now be very careful when you throw out the rubbish. You've got to make sure you don't put something that's not rubbish in the rubbish bin. But when I look at this, it's the +3 that irritates me. If that wasn't there, then it's not very different to the earlier example. So I'm going to toss away the +3, and I can do that using an inequality. So just take note of this little very useful trick. I toss away the +3. Is that valid? Yes, because n squared plus 3 is bigger than n squared. And so in the denominator, 1 over that is less than n squared. So just note that step there. Just note that step there. You throw away the rubbish, which is 2. Now I go back and use the fact that I want to get everything now in terms of capital M. And so I've got 6 over n squared. So 1 over n is less than 1 over m. So this is less than 6 over m squared, because n is bigger than m. And so taking 1 over the square of each will give me 1 over n squared is less than 1 over m squared. Finally now, I've squeezed this difference down to something simple, and I wanted it less than epsilon. So at this stage, I just put that equal to epsilon, and I'm going to solve this now for m. So I'll just do a little calculation down the bottom here. So if I turn everything upside down, I get that. I can multiply the 6 across, so I get 6 over epsilon, that's m squared, and now I can just take the square root. So at this stage, I'm now going to solve this for m in terms of epsilon, and then before anyone looks, I go back up here and I'm going to write 6 over epsilon. And I've now satisfied the definition. The definition was, I tell you how wide the band is, I tell you the epsilon, you tell me how far I go. So I put in, if epsilon is 0.1 or something, then I say 6 over 0.1 and take the square root of that, and that's how far I have to go out. So that if I go beyond there, the difference between the sequence and its limit is less than, I've got lots of less thans here, less than epsilon, and that's the width of the band. So the definition is satisfied. Now again, you should go carefully through that example. I'll do one more, and there's lots of these in the tutorial problems, but you should go through carefully that example. Make sure you follow the steps. In particular, this is a tricky step here, where I toss away things that I don't want, simply by using inequalities. Now you might say, well, yeah, well, what happens if that was a minus here? Then you can't do that. Well, there are ways around that, but we're not going to worry too much about that. I will make sure in all the examples that we do that the obvious inequality just works. I'm not going to give you ones where you've got to use some clever trick, or at least expect you to be able to do one of those. Okay, I wanted to do a third example here, and again we're going to prove from the definition that the sequence n squared minus n plus 3 divided by n squared plus 3 has a limit of, well, you should look, before looking at this, have a look at this. You see where the money is on top, it's n squared, on the bottom it's n squared, the rest of it's noise. So as n gets very big, that's where the money is. It's n squared on n squared, which is going to 1. So this has a limit of 1 as n goes to infinity. And here is the proof of this one. Again, that's what we're trying to prove, that this limit is 1. And again, I begin with the usual mantra, given epsilon bigger than 0, put m equal to, I'm not sure yet. Then if n is bigger than m, we look at the sequence minus its limit. Once again, we put everything over a common denominator. So I get n squared minus n plus 3 minus n squared plus 3. And happily nice things happen. The n squared minus n squared cancels. I get 3 minus 3 cancels, and I just get a minus n left over n squared plus 3. Take the absolute value, so that's going to be n on n squared plus 3. And once again, what do I want to get rid of? That plus 3 is a pest. So I'm going to toss away the plus 3. I'm going to put out the garbage. The garbage is the plus 3. So I toss that away, and I can do that using an inequality. Because n squared plus 3 is bigger than n squared, so in the denominator this is less than. So make sure you follow that step carefully. So you toss away the rubbish, and now n squared on n, well that's just 1 on n. And finally I need to get everything in terms of m's, so I again go back to the fact that I know that n is bigger than capital M, so this is less than 1 on capital M. I wanted the difference less than epsilon. Once I've got everything in terms of capital M's, I simply once again put that equal to epsilon. And before anyone looks, I solve this for m, turn both sides upside down, I go back and I shove in the 1 on epsilon. So again, the definition is satisfied. I tell you how wide the band is. So if the band is, again, if it's 0.01, then I take 1 over that, which is 100, and that means I have to go out to beyond the 100th term before this sequence is within 0.01 of its limit. So we take the sequence minus 1, we just trace it through, is less than epsilon, less than the width of the band. And that's the definition satisfied. So that's going to be our basic skill that we're looking at here. And I will do, I'll do one more example. This one is a harder example. This is harder than I would actually expect you to be able to do, but I wanted to show you that these can get quite complicated, and I'm going to show you a couple of complicated examples. So here is our next one, and this is a more difficult example, probably harder than I had intended, but we're looking at the limit as n goes to infinity, square root of n squared plus n minus n. And we're going to work out what this limit is firstly, and then I'm going to give a proof that the result is correct. And in fact, I might, given the time, I might leave that to the next lecture. So we'll finish this one off in the next recording.